And so all these kids in our class were just like drawing random trusses and then by hand, like writing out all the forces and seeing like, would this bridge work? And I was like, I know machine learning. I was in machine learning labs. I've worked with a lot of like optimization algorithms. I'm like, I'm not doing this by hand. So I wrote a genetic algorithm that would just like do random variations of the truss layout until like, and I left it overnight. And eventually the next day, which was actually the day it was due, it actually spat out a bridge that a truss a geometry that was 75 newtons. I just want to build a jet engine and see how hard that is. And I want to apply machine learning to try and help me do that. Like you can describe exactly what you want and it'll give it to you. That's exactly what I want to do. Like I want a fan that is 10 inches in diameter that has the maximum amount of airflow. Now give me the CAD and I can just 3D print it. That ideally would be the promise.
I think we met, was it last week at the Founders You Should Know salon? And I had seen some of your work online and I thought it was really cool. So you're working on this AI generative, is it for jet engines and...
Jet and rocket engines. Yep.
Jet and rocket engines.
Specifically the turbo machinery aspects of it right now. So pumps, compressors, turbines. But yeah, that's mainly what I've been doing so far.
So I'd never seen anything like that. So it kind of piqued my interest and I watched your YouTube video about it. But then also, then we sort of got talking about some of your other stuff you were doing, your background. It's like interesting kind of your journey. And so I wonder if we could actually just back it up a little bit to learn more about you. And then we'll get into the AI generated, kind of engines and turbines in a little bit. So like you were telling me about your piano playing history in Europe. What can you set me up? What's that all about?
Yeah, that was in high school and early college. So I've been playing piano since I was 8. And around the time I was in high school, I started to play more at like concerts and recitals. And around that time, I was playing in like Finland and like Germany and like different parts of Europe. And so that was a very interesting experience. I got to play at like John Sibelius's house. We met like a bunch of like really famous Finnish musicians, bunch of Finnish art museums. I got to play there, and it was just a really cool experience overall, I think.
And were you thinking about potentially pursuing the arts or kind of piano performance as a career, or did you kind of imagine it was always a bit of a hobby, or how do you think about how it fits into your life of work?
I think I was always interested in the arts, but I think mainly for me it was more of just an outlet of expressing myself, and I think it had its moment, but I've always been really interested in computational like everything. Like when I first started out, I was like 12, 13. I think I just saw the first Iron Man movie and I wanted to build Jarvis. And this was actually way before the modern like Alexa, for example. I remember in those days I was like, I think I was using like the early Google voice recognition API.
Right. Yeah.
And I was first, this is like before I ever knew anything about programming, and I was teaching myself Python. And I took that early Google voice recognition API and I built out a little like assistant, and I would ask you questions like, what's the weather like? Or what are my files on my desktop? And can you delete that file for me? So like a very simple Google Assistant almost type thing. And then I started building hardware. I actually wanted to build like a little HUD that I would put around my face. And so I got a Raspberry Pi and like a little display and like had like a bunch of reflectors, so it would actually reflect into my face. So I was like very interested in like HCI early on. And then eventually I got more into engineering as I got more into like electronics and that kind of stuff. And so I wanted to school for computer engineering to actually see how do you build these computers that fascinate me so much. It's been a wild ride. So it all started just like very interested in computers from the start. And
right. So it sounds like a lot of computers and software is in your background, but the problem you're approaching has some domain specificity and kind of mechanical engineering, right? Would that be
Yeah.
generally
Yeah. So it's interesting. So the story I kind of got to jet engines and all the stuff in aerospace. It was actually just in engineering in general and mechanical. It kind of spurred like last year of college. And I put off my statics class towards the end of school. And one of the assignments was to build a bridge with a truss. And so there's like a lot of ways you could go about this, but the main way is that use this thing called moment of joints, where like essentially at every point in the truss, you have to find the equilibrium forces that make it up. And you have to design a truss such that it can support a minimum load. So it was like, I think 15 Newtons or something like that. And so all these kids in our class were just like drawing random trusses and then by hand, like writing out all the forces and seeing like, would this bridge work? And I was like, I know machine learning. I was in machine learning labs. I've worked with a lot of like optimization algorithms. I'm like, I'm not doing this by hand. So I wrote a genetic algorithm that would just like do random variations of the truss layout until like, and I left it overnight. And eventually the next day, which was actually the day it was due, it actually spat out a bridge that truss geometry that was 75 Newtons. And it was like the highest, I think, in like the class's history. And at that moment, I was like, I'm very interested in applying machine learning towards complicated engineering problems. This is so interesting. Like you can use it for a lot more than just like weird art and like ads and stuff like that. You can actually use it to solve very interesting, complex problems that interest me. And so how I actually got interested in aerospace is I wanted like something to apply something like this towards. I was very interested in the design reversal process. And so I actually came across this video by Found and Explain about this plane called the Star Raker. And it was essentially a way to get to space that was way cheaper than like the Saturn V that was like its predecessor. And
you said called Star Raker?
Yeah, Star Raker. Okay. It was by Rockwell. It was designed by Rockwell before the space shuttle kind of, took its lunch and it kind of failed because you need multiple stages. And the idea of this is it was all one stage. It was it was like a space plane. And I think it had like 4 or 5 different jet engines and then 3 rocket engines. And the idea is that you have all of this oxidizer in the air. So you don't need to carry oxidizer. And you also have, in its place, you can actually carry a lot more fuel. And the nice thing about planes is that the lift force, you don't actually have to support all your weight with propulsion. So that means you actually need a lot less fuel as well to get to the upper atmosphere. Once you get to the upper atmosphere, then you just use normal rocket engines, and then you can, get to your target with you could carry a lot more payload because you don't need as much fuel and oxidizer in this kind of format. And like people have their ideas like space planes won't work because XYZ. But just that kind of architecture of that video of like that kind of space vehicle, it like interested me a lot. It was like a very interesting engineering problem. And so eventually I was like, okay, I just want to build a jet engine and see how hard that is. And I want to apply machine learning to try and help me do that, like the same way it helped me make that bridge. So the way I started out is I just got like 3 or 4 different textbooks on fluid mechanics. And specifically, there's this book that was very useful. It's called Fluid Mechanics and Turbo Machinery by S.L. Dixon. And it literally just walked me through like step by step. Like, okay, you start out with these governing equations of fluid mechanics and thermodynamics. And it kind of just went step by step. And then like eventually went into like how different flow angles can affect efficiency and like all kinds of stuff. And eventually I was able to make like, I did like all the homework problems and I just like confirmed it with like Chegg. And eventually
you were doing all this like additional research. This was after you sort of made the observation in the class that you could sort of do your lab assignment exactly with this. Then you sort of were you going? This down is after graduation. You wanted to learn more about potential things that you could also do with software and machine learning.
Yep. This is essentially the application that interested me the most out of all the engineering disciplines that I wanted to apply something like this towards. So I went through, did all the homework problems, like this whole like notebooks full of like, a bunch of like all the homework problems I did. And eventually I was like, okay, I want to take these homework problems and just make them programs so that I can actually like, have an input and an output that ideally is like the input being the inlet conditions of like, let's say a compressor, and the output being like the geometry of how to make that thing, like the shapes of the blades, the angles, the just overall like the compressor, like diffuser shape, like where it gets or just like the shape of the compressor gets smaller and smaller. So like all those different geometries, you actually use like fluid mechanics to like as a governing equation to get those geometries. And yeah, so eventually I got everything, and it was like a very empirical form of like how to find those geometries. But then I ran into the problem, like all these kind of equations are just assuming there's this concept of loss. And in an ideal world, you want to assume there's no loss. But in reality, there's losses through like stuff like stall, which is, high drag that could cause like a lot of inefficiencies. You could have like, for example, backflow. So there's all these concepts of loss that your geometries can be changed to minimize that loss. Right. And the problem is like there's all these loss models that people make and that are just a bunch of like equations that the problem is like with all these equations, you have to keep everything else constant. Like, so say like you have like the length of the blade. Everyone says like, okay, keep the length of this blade at like this constant length, depending on these certain parameters, or like the spacing between the blades, keep it constant for the spacing, and only change, let's say, I don't know, the thickness of the blade, right? So the problem with all these loss models is that like it's very like there's only one variable you're trying to optimize, but in reality you can optimize like a bunch of different variables. And the problem is just human beings aren't very good at like managing like really high dimensional problems like that. And so eventually I was like, okay, this is where machine learning can be used. And so right now I'm using simulations, which is a way of actually simulating the environment that this blade would be in, and machine learning to then run through a bunch of different design iterations until it converges towards a desirable result.
So are you picking a lot of times, are you taking a particular design that already exists and trying to like improve upon it? Or are you sort of starting with some kind of de novo design that you have in mind, or kind of a potential initial condition that you want to explore from?
Yeah, so there are open source compressors. I think there's like the Rotor 97 or something that's like that NASA released. There are like open source specs for those. I'm not trying to do that so much. I'm actually just trying to get the conditions that I want, and then just give it, and then it just figures it out.
So what's the kind of constraint that you put as the goal for what you want it to see?
So the constraints are a few things. So like, for example, the simulator can give you the efficiency for each stage. So for example, if it's something that's very inefficient, then that's something that can be minimized. So that's a constraint.
And inefficiency could be is that in like materials or in just like
inefficiency
execution?
in the flow? I haven't gotten to material properties yet. That's like a whole nother ballpark. Right now I'm predominantly kind of focusing on like the fluid, like the flow and how efficient the flow is around geometries. So just essentially the fluid simulations. But yeah, like I think so that the constraint would be like efficiency. Another one would be you're trying to maximize the pressure out. So if you have a really high pressure rise, then maybe that's something that, for example, a compressor that would be advantageous. But at the same time, like there's also this concept of loading too. So like the loading of the blades, like you could have like a lot of stress if you have like a lot of compression, which, goes back to the material properties. Maybe that's not so good. Maybe you're just going to break the blades off if you compress too quickly. So there's other constraints that you'd put in place to essentially try to get something that is like advantageous for a lot of different multi-objective objectives. So
today, when people are typically taking like a compressor design, do you start within like maybe a large organization that needs a compressor with a certain set of characteristics, and you start trying to iterate towards those goals?
Yeah. So traditionally, what I've seen is like there's a lot of like you usually start with like this thing called so first you want to like get the specs. So you do a design study of like what those specs should even be. So like if you're trying to design like a jet engine, let's say you want like a certain amount of force coming out of it, then you say, okay, I'm going to need this many Pascal compressor for compression. I need this this much flow into the fuel for combustion. And so that then after the design study, then you get the specs of like, okay, these are the inlet conditions. This is how much it should compress. This is the mass flow of like how much fluid should be going through this compressor. And so once you get those spreadsheets, there's like empirical methods that they start out with. Usually this is called mean line design. And usually they use like MATLAB or some sort of spreadsheet to then kind of ideate like how do you get from these specs to some sort of geometry that makes sense, like the angles of the blade, or like what kind of airfoil you should use based off of conventional wisdom, which, you know, I'm not doing that. I'm actually, I actually have a tool that parameterizes airfoil. So you can try like a bunch of different unique combinations instead of just like a NACA 65 series, which is like a traditional kind of hard-coded airfoil series. And then,
so it sounds like similar to what you did with like was it the bridge example in school where you kind of discovered...
So you just keep tuning these points until you get something that is advantageous.
But you end up with like very novel approaches because you're kind of breadth first search exploring.
Yeah, it's very open-ended, which is the idea. I feel like a lot of the design process I've seen, at least with compressors and like some of the stuff in aerospace, is it's almost like a very defined process, and then you get something that's like based off conventional wisdom in the past of like some simulations some guy ran like the 50s, made like an empirical model out of it, and then from there they use simulations. But I'm just saying, like, why not just start with simulations and then guide? And I feel like it made sense then, right? In the 60s, we didn't have like giant supercomputers. We didn't have like all the resources we have now. Like, and same thing applies for machine learning. Like, neural networks were around for a really long time. It's not until recently that we're actually able to do like large language models like what we see right now. Like, so I think right now it's like the same sort of approach should be to, like, we have the compute resources, so why not just alter the geometry, verify with simulations, and then do that cyclically with like minimal governing equations. And sometimes you can find some really cool things that apply.
So is the current process, like before we have this generative process that you're pursuing, are people doing kind of manual tweaks and then kind of cutting that and putting it into a simulation and then taking the outputs and using it to generate kind of new human generated creativity? It's kind of like a two-step process.
Yeah, so typically they have an empirical process where they kind of get like a base geometry, and then they run simulations to kind of like they refine, like, so they have a mesh once they go into the simulation, and there's a bunch of coordinates in the mesh, and they try to like kind of, perturb those mesh shapes a little bit, but it's like, it's not like a big change. It's like it's enough such that, like, maybe the airfoil goes down a little bit. But they're iteratively doing that until they get something that is more optimal in like a more simulated environment rather than an empirical environment.
And they're doing it with some hypotheses around, maybe there's some experience they've had before that you could.
A lot of it is based.
Tweak.
A lot of it is based on conventional wisdom. Like, they built a jet engine in the past. They have like the specs for that. A lot of times they just, the same way we do with software, where you just fork that and then make some minor changes for whatever you're trying to accomplish. But as far as like actually trying to make something novel, it's it's a lot like more like it's a lot more like define like the way they do things rather than like an open-ended problem to try and discover something different.
In the general, like, is there a separate area of research, or even maybe within a commercial environment, where people are encouraged to like kind of explore the crazy ideas around here? Or is it everybody's kind of marching toward, I mean, I guess these are big capital expenses, and so you probably need to reduce some of the variability in exploration, some of, kind of early stream. So is that something that happens today with the kind of radical idea exploration, or is that more kind of excluded?
So I think
cost structure.
I think that's the biggest thing, I think, which is like R&D is probably the biggest cost with a lot of these aerospace projects. It's, I think you can kind of see that like almost with like Starship, right? Like, they're able to like kind of pump out 3 different launch vehicles like weeks or months apart, which is like a marvel of manufacturing on its own. But the biggest thing is that like, a lot of that is like designing and paying the engineers to actually do that R&D is actually a lot of cost. And once you actually have a manufacturing process, you can actually create an economies of scale after. But I think design is like, and R&D is like a really big cost that can be automated for sure.
So does the manufacturing process, like let's say you were to come up with a radical design that nobody's ever thought of and maybe in their traditional methods is not worth exploring, and it turns out to be really productive in simulation, then you want to move it to manufacturing. Are there certain constraints that you would want to use on the space of exploration because of what manufacturing can handle, or are there other changes happening in the manufacturing process?
So that is another thing, which is how do you actually manufacture a lot of these things, which I'm actually exploring as well, because I'm actually getting to the point where I want to like start doing real world tests very soon. And so there's like a lot of things where if you have very complicated shapes, obviously that's going to be a lot more expensive to manufacture. For example, like the blades, a lot of people are moving towards metal 3D printing. But I think in the past, what they would do is they would have little like masks of the blade as a cast. They would cast it. And, that worked for a while. But there, like, for example, with turbine blades, there's actually a lot of these cooling channels that actually go through it. And so you have a lot of complicated, intricate, like tiny holes that go through these blades that like metal 3D printing is actually really great for. But it's also a lot more right now expensive. So sometimes, like I think the biggest thing is like if you have like a very like complicated design, maybe that's going to cost more in like the short term, because those manufacturing processes for making something like that haven't been invented yet, or they're expensive as is and they can be reduced. So
and in your mind, is that just something like if you were to discover new designs through these new methods, you'd be okay just deferring how the manufacturing, it's a whole other set of problems, but you're kind of not trying to constrain by what's possible in manufacturing. You're sort of open-ended exploring the loop between design and simulation? Yeah,
right now it's predominantly design and simulation. I think eventually, like the thing is, I'm not actually too worried about manufacturing right now, because the biggest thing is the blade shapes. That's the most complex part about what I'm doing right now as far as manufacturing it. I think I've been talking to a few people that do metal 3D printing startups, and also there's other ways you can make these blades too. Like there's 5-axis CNCs, there's different casting methods. So I think the blades, since there's such like a weird shape, there's like twists and different angles and like shapes of like the actual airfoil itself. It's something that I think is going to be like that's probably the hardest part to manufacture. The rest, like the casing and like everything else to put it together, that can all just be 5-axis CNC milled like pretty easy with just some aluminum or something like that.
Right.
So
and is the generative step that you're using now, is it related to some of the stuff that maybe we see online with large language models or any of the generative art stuff? Is it similar techniques or other ML
so
stuff?
as is it's using this thing called generative CAD, which is generative in the sense of the buzzword everyone's using right now is mainly referring to like transformers, LLMs, where essentially you give it a prompt and it can predict the next word. And that's why they call it generative. And they create something that can predict something, generate something that, is based on a really large model. Right now, the way I've kind of targeted it is with generative CAD is you define the problem with code. So for example, I say I have a blade and it has a shape, and this blade gets extruded and twisted into another shape. And so all of that is defined in a parametric model. And what a parametric model is a way of defining a geometry with some algorithm. So in my case, it's just code.
But the result is you change some parameters, then you get a slightly different twist that may have a different performance characteristic within a simulation.
And then you just resimulate that. And so that's what I mean by generative as is. Now, there's something I'm working on that I'm actually pretty excited to explore, which is right now I'm just doing Aerospace, and I'm just defining the parametric model manually with like proportions and angles, and then trying to tweak those until you get something. It's always valid, which is nice, but it's you have to manually define that parametric model. Eventually, what I want to do is just having like a config or like a spec where you can just say like, hey, there's a disk and it has a bunch of it has like a polar array of points, and each one of these points I want to have like something sticking out of it with a shape, and that like it's like a very, very versatile way of defining a geometry that if you make a structure like that, I think you could give something like that to an LLM like ChatGPT, and it can actually convert just layman text into that structure. If you can structure your model in a way, your parametric model in a way that an LLM could just generate, then you can just use text to generate something like this generative CAD, and then you can tweak that the parameters of that parametric model and then use simulations to refine it. So you can actually.
So I had thought that maybe you were kind of just taking some initial conditions and having ML explore the kind of a broad set of ideas that could be started from there. But it sounds like maybe that's part of it, but it sounds like you're also trying to get the connection point between language so that would people be hypothesizing a new idea and then they wouldn't have to know how to use CAD tools? They could just be like, make this blade twistier and see what happens. Is that kind of what the interface would be?
Yeah. So eventually the interface I want it to be is something like that. It's going to take a lot of work to get there though. I want to have it so it as is right now. The easiest way to be doing this is like, like, okay, for example, a fan, right? It's just a disc with a bunch of sticks sticking out of it essentially. And those sticks are like shaped in a way such that air can flow through it, and it guides air through that channel. So I want it such that you can just describe the problem and it'll generate the parametric model for it, and then it'll simulate and refine it, like you're saying, which is what I'm doing now. The part that I'm doing now is I already defined the parametric model manually, and then I'm simulating it and refining it until it's optimal. But eventually what I want to do is making it very versatile, so you can just have a config file or use language to generate that config file of what the parametric model is. And then you could just tell it, okay, this thing spins and I want it such that in the simulation, it, like, for example, a fan, I want it to have the maximum amount of airflow, and it'll figure out what the shapes, and you have to define like the shapes of the sticks are the things that I want you to optimize, and it'll do it. That's eventually what I want to do at the end of this. I'm right now trying to like stick with like just the optimization process. And then eventually, once I get that towards something that's promising, then actually create a way you can just use language to describe the problem altogether.
And actually that sort of brings me to another question I had about this whole project, which is sort of, there's I think a very kind of contained or narrow scope of starting point, fairly narrow because it's actually achievable to do, make real progress. But it seems like it could go into a lot of different directions. Like, we talked about manufacturing and we're talking about using language as an input. And so, just sort of like zooming out, I wonder, how do you see this project sort of, do you already have a hypothesis on what you think it looks like, if step 1 is successful, step 2 shows promise, like what does it look like, in step 10 or 15 or something?
So assuming, let's say 10 years down the line or something like that, where everything works out, eventually I hope it will just be something where you can describe exactly what you want and it'll give it to you. That's exactly what I want to do. Like, I want a fan that is 10 inches in diameter that has the maximum amount of airflow. Now give me the CAD and I can just 3D print it. That ideally would be the promise I want to see at the end of this.
And who's doing that input? Is that somebody who today would be on like a design or engineering team within a
it could be even a normal person. Like, let's say you have like, I don't know, someone wants, I don't know, like I want to make it so really anyone, you don't need to actually be an expert to use something like this. I think for like a normal person, maybe you want like, I don't know, a water bottle that has like a way that you can like drink the most amount of, I don't know. So like something that like anything you want that you could describe, I want to make it such that anyone could use.
I see. So almost
right now,
these examples seem like almost like the water bottle is almost like a consumer product idea, but it sounds like the jet engine or turbine idea is, more likely a industrial kind of application. So is it just that industrial applications a place where you think you can create a lot of value today, or sort of really move the art forward?
Yeah, so I think the industrial value is probably right now the biggest, like user of this right now. Because obviously, I haven't gotten to the point where I've used language to use it. Also, engineers are really good at actually describing problems. I doubt a lot of people know a lot about the stuff they use and how, like, describing how they actually work. So probably the biggest use would be engineers early on.
So is it that you're going to change their workflow though? Because you're saying a lot of people might not know.
Yeah. So exactly.
Like how tough their work is to.
I think it is about changing their workflow. Like the same way, like, okay, everyone uses ChatGPT now. I use it a lot for programming. Like I use ChatGPT a lot. I just used it the other day to like generate some Python code to run a data set. So if they could, I think the biggest thing is like, fitting that into their workflow. Like if you, for example, were trying to design something and you said like, okay, I have this thing, this is the problem. Can you generate like what this parametric model does? Maybe it generates a library for you to actually run that parametric model of the geometry. And then you can plug that into simulators and or yourself, or actually just get the thing to run it for you and have everything automated. So I think that's the biggest promise, which is like automating the pipeline of like into their workflow of like everything they do.
And do you think that are there larger companies today who might already be either exploring these paths, or that you already suspect are open to adopting such a path if you can prove that it works? Oh
yeah, I 100% think. I think generative CAD and just the whole space of like going straight from spec to CAD is like a very like, it's actually getting right now like it's a very recent thing. I think like CAD Query, the tool I'm using for generative CAD, only came out like a few years ago. Like I heard like from people, like a lot of people from different CAD companies are leaving to start their own generative CAD companies, and ML and CAD. So I think that's going to be a very big field, like especially right now with everything.
And so was CAD Query, was that one of the first kind of programmatic interfaces to being able to do CAD?
I think before CAD Query, there's this thing called OpenSCAD, which was like its own language. And I used OpenSCAD, and I think that's been around for a bit, maybe like 5 years or so. It wasn't very, I didn't like it a lot. It was not very intuitive. It was really slow. I think everything would run only on one thread. It was just not a very good experience. Actually, I started this project out with OpenSCAD, and it just was not a good time. I think CAD Query, the biggest thing they had was they started out on this thing called Open Cascade, which is like a very popular 3D manipulation library that's native as well. And it's also CAD Query as a syntax. It's just very easy to use. Like it's very like you could just define a work plane, put like say a square, say extrude that square, all in code, and it's like very easy to work with. It takes a little bit getting used to just putting parametric models in your head and understanding how to code them, but it's a very interesting process. Like how you can at this point I'm probably faster coding CAD than using a UI.
And so, is CAD Query like an open source project, or
CAD like Query is open source. Yep, it's a library, open source library. Yep.
And do people contribute libraries of like the components that they built sometimes?
Yeah, there's a lot of really interesting libraries. Actually, there's this person, Roger, I work with a lot, and he creates this whole library that has like every fastener you can think of. Screws, like chains, like really anything you want, like heated inserts for like putting screws in. There's a whole library for gears. Like I need a gear with like 10 teeth. It generates the gear for you. So like there's a whole community of people making libraries for this whole generative CAD space.
And do those all live on something like GitHub, or is there like GitHub
all
equivalent
GitHub
for these?
And also the nice thing about CAD Query that was really nice comparatively to OpenSCAD was the Discord community is just insanely helpful. Like you have a problem, they'll get back to you in like a matter of minutes of like what you should do. They work with you to like, and just like completely for free. They just help.
They're just people who are passionate about the tool, right? They just want to help.
Yeah. And I've never had an online community that helpful before in anything. Cool. So it's probably been like, I think that was like the biggest thing, which is like, I needed help. OpenSCAD was really slow. I needed like resources, none of that was there. And so CAD Query was really kind of leading it on that. So.
And on the kind of the non-coding or scripting side of it, is Autodesk like far and away the leader at kind of the UI based CAD tools, or are there other open source ones?
So Autodesk is probably the leader. I think SolidWorks is not too far behind. I actually was using Autodesk before CAD Query, and kind of the thing that was the I guess the straw that broke the camel's back for me was like they started really starting to restrict stuff for free. That was free. For example, step outputs on Fusion 360, and they just slowly started like cutting stuff out of the free stuff. The biggest one that I just like never went back to Autodesk was I remember the thing that got me into CAD was this tool called 123D Design they made, and like everyone started using this. It was just so easy to use. There's like, I think 10 different functions on it. It was literally just like place a shape, place a polyline, extrude it, twist it, whatever. It was super easy. And so like everyone was using this like a few years ago. And then all of a sudden they just killed it. They just killed it because everyone was starting to use this free thing. But like, I imagine it was starting to take like a cut at Autodesk's products
like
that were making.
Autodesk had built the free thing. It was just kind of meant to be maybe a marketing
it was just
tool.
It was just a baby project they released, almost like Microsoft released VS Code. Except Microsoft actually like embraced VS Code and everyone's using it now. Versus,
was that true when Microsoft started VS Code? There was no intention for it to be a real product.
Yeah, actually, my brother was there when they started, and he's actually the one who told me super early about it. And like it was kind of started as like a baby project. I think some guy just wanted some tool that was just easy to use, didn't have a lot of clunkiness, and it was based on Chromium, so it was just really easy to just set up with like Electron. Wow. And then a lot of people were like, "Wow, this is like really nice." Like, and like has like really cool extensions that I could use with it. So, like I think that was the problem, which is like everyone was using 123D and they killed it, and they were like, hey, use this other thing we made, like something CAD, and it was just in the browser and it was just awful. It was it was like that was baby software. It was like so bad. And so
it sounds like Autodesk has like the big commercial thing that everybody uses, and then CAD Query is like this. Is it like a command line interface scripting kind of library?
Yeah. So CAD Query, the ideal setup is you have like a VS Code window where you're coding the CAD model in Python, and then it has a visualizer which you can view in VS Code or on the browser, and it'll compile the code and then put a visualization of what it currently is, and then as you code it, it'll update how it looks.
And is there like, let's say somebody who doesn't want to use, or maybe they don't have Python skills, or they don't want to do the code interface, is there an equivalent kind of open source kind of Autodesk style tool that they could use on top of CAD Query?
Yeah, there's been a few implementations where they try to like go from visual back to code. They're pretty beta right now, but there were attempts to do something like that. I think the biggest thing is that like that's not really their model. Their model is kind of just going from code to CAD. And the nice part about it is that like if you had like a different size, for example, of something, or a different diameter or whatever, you can just make all those parameters to the function. And so even if something is in code, I imagine a normal user can use it in the sense where they just take the code and they just adjust those parameters.
Right.
And if they actually have to code anything, they just adjust the parameters.
And it's more legible. You know exactly how the thing is getting constructed because you know the code. Exactly. So even if you can't read the code
is very easy to read. So
almost anybody who could use the full, I guess, windowing system or whatever Autodesk uses could probably at least
because a lot of the function names are like exactly. Actually, I could probably show you a little bit of it. Let's see.
Sure.
If you run this, it should display what that box looks like right next to it. And yeah, it's a little lag because I'm sharing screen.
Right.
But yeah, it goes through. Okay. Yeah. Once it displays it the first time, it's usually good. So so this is the box or rectangle. So the nice thing is the reason why they call it CAD Query is they have these things called query selectors. And so the nice thing you can do is you can go here and say like, okay, I want you to select all the faces that are the greatest Z face. In other words, like that's this top part.
Yeah.
So select all the greatest Z faces. And then I want you to make a work plane on top of it. And then once you make that work plane, let's say we want to put like a hole that cuts through this whole thing. Like maybe you want to put like a pole through it or whatever, right? So what you do is you say like, okay, create a circle. Let's make it maybe 2 millimeters or 2 millimeters in diameter or in radius. And then you say cut through the whole thing. So you say cut through all. And then you run this. There you go. You got your hole. But this can do a lot more other things. Like let's say you want to select all of the okay, like another thing you could do is maybe you want to make a smaller you want to make like 4 holes here, right? Maybe you want to do something like that. So what you could do is you could make like a rectangle, and let's make it like 5 by 5, so it's like half the size. And you want to say that this is for construction. In other words, like you don't want to like store it on the stack. You just want to use the coordinates of this rectangle. So you want to use it for construction. And you say vertices. And then you say the same thing, circle. Let's make it 1 so it's small. And you say cut through all. And there you go. So now it just created 4 holes of this sized rectangle, and each vertice. So these are all query selectors. So like just querying. So like the way that you interface with this is instead of a UI and clicking the face or clicking these points, now you query just the face. So you say like, okay, the greatest Z face or the greatest Z coordinates, and then take those and do something to it. So that's a really cool way of interfacing with it. And at this point, I've become like pretty efficient with it. It also has like a bunch of other features. Like if you want to chamfer the sides of this, let's say by 2.
What does it mean to chamfer?
You kind of like flesh it, like you flatten it out.
Oh, okay.
So like it has like all the features you have with CAD, but as functions, and you can just do so many cool things with it to the point where I've just like, I've created like literal jet engine parts with it. So
what we're looking at right now is kind of the hello world of how CAD query works, right? And now we're kind of getting into this is a jet engine you already have made before?
Yeah, so this is a compressor that I've been working on. This is an axial compressor assembly, and so everything
starting from the beginning of like an initial basic, well understood compressor.
Yeah, so this is just starting from a very, very high level spec. So if you want to look at the spec, it's very, very high level. So if we go here to Mark 1, it's literally saying like, hey, I have a compressor. This is the mass flow rate. This is the pressure ratio. A bunch of inlet conditions, how many stages you want it to have, like even like what fluid. Like I've gotten it in this latest version I'm about to release. Like you can define like, oh, I want a compressor or a pump for water or whatever, right? So you can define actually the fluid type, and there's this library that will just take that fluid type and then do all the thermodynamics for that specific fluid. And so you give it to this thing, and right now what it does is it takes it in, and it has this initialize step where it just gets like a base geometry of like, and this is like all stuff you'd see in textbooks of like how to start out with like the geometry you want for a compressor. And so the next step is taking that initial geometry and then actually refining it into something that is optimal. So that's kind of like the next step. And I've already written a bunch of libraries that you can take in, like you can automatically mesh all this stuff. You can automatically run simulations and all this stuff. And eventually the goal will be to like get the parameters that are optimal. So,
and is there a certain set of parameters that you're tweaking or sort of sending through this kind of exploratory process?
Yeah, exactly. So the parameters I'd be tweaking ideally would be these parameters here. So you go through, I have this B-spline airfoil. And so a B-spline is just a way of like creating a curve with control points. And so the things I'd be tuning are like the angles of the inlet angle and the outlet angle. I'd be the stagger angle, which is how much it's twisted, the thickness of the top and the bottom. So how thick are you from this thing called the camber line, which is the general shape of the center of the airfoil, and then the proportions of like how much the angles at the inlet and outlet should affect the shape. And then the last thing is the chord length, which is like how far how far apart are the like how big is the length of this airfoil like axially.
And are you just running like effectively a brute force exploration of all of the combinations of these, or are you doing like some sort of randomization, or are you kind of hill climbing and trying to find improvement?
So to start, it's going to be using genetic algorithms, which they kind of start a little bit as brute force, but they recognize like different patterns to like kind of narrow in on like an optimal valley. But what I'm going to do is every single time it runs a simulation, I'm going to store that simulation. And so the thing I want to do long term is you have so much simulation data for so much different geometry data that you could actually train something like a convolutional neural network to just like from all the data you've seen in the past to just predict what that geometry should be. So you're in like the general right area. So when you write the genetic algorithm, you have to do a lot less iterations to get there.
Right.
Yep.
And is the simulation step like relatively free from a compute and cost, like speed time perspective, or is it?
So it depends.
To be a little bit smarter around that. Yeah.
So let me actually show you the next part, which is I have this other library I have called Parafoil. So you can kind of see this for yourself when I run it through. So right now I'm doing 2D simulations, and 2D simulations are like, they're so 2D simulations are a lot less computationally expensive because it's one less dimension, and you can get away with like getting the general like behavior of the fluid patterns for what you're trying to solve, but it takes a lot less compute. So I can probably run through something in this nature of like, like some of the turbo 2D simulations in like a matter of like maybe 30 seconds. But eventually,
so a given configuration of those parameters outputs a potential design that then takes about 30 seconds to evaluate in sim.
In the sim, yeah. And so that's the problem, which is like just using a genetic algorithm, which is you have the latency of a 2D sim, which eventually I want to do 3D sims, and you have to like brute force essentially like hundreds of thousands of times until you get to something that is even remotely optimal.
And presumably the 3D sim is much more,
much more
complicated in time. Like
time. 3D sims take like sometimes days for one.
Oh, for one. So the same thing that's 30 seconds in 2D could be days in 3D. Kind of same complexity.
Yeah, exactly. And so the other thing is like, I saw this guy, he made this Lattice Boltzmann simulation that you can actually run 3D simulations in like a matter of like 45 minutes or so. The problem is Lattice Boltzmann is like in some applications is not too accurately reflecting what the behavior should actually be. But it can give you general like patterns of like what the flow should be like. Also Lattice Boltzmann, it's like, it's not really refined around like some of the like, like really close to the blades, like the edges. Whereas in a lot of 3D sims, you can like refine those edges. I know people that you could probably refine the edges also in Lattice Boltzmann, but it's typically Lattice Boltzmann. Like a lot of people just give it like a CAD file and it just runs.
And Lattice Boltzmann, is that a particular software product or a technique or approach?
Lattice Boltzmann's a technique for simulations. So that's like one way of evaluating
the Lattice Boltzmann. So and you were telling me about how Lattice Boltzmann is a kind of a technique as opposed to like a particular software product, right?
Yeah. So Lattice Boltzmann, so software product would be ANSYS, which is like a simulation suite that has Lattice Boltzmann as a method for simulating. And
that'll help you speed up a 3D simulation from
so Lattice Boltzmann, because it's more approximate, it's a lot faster. But for RAND simulations, they're like I don't know exactly the details, but it's a lot more accurate of like how something would actually behave in real life.
And so we've been talking a little bit about the some of the kind of goals of the project that you're working on right now. And, I wonder if you could give us a little bit of flavor of what is this? Is this like a is this like a hobby project? Is this like a passion project? Is it, I think it's fully open source. I'd love to hear how that kind of fits.
Yeah, so it started out as a passion project for sure. Everything's open source, and I'm mainly working with a bunch of researchers at like Stanford and like specifically the Aerospace lab, design lab there, the SU2 Foundation, which is the simulator I'm using right now. Like a lot of people, I'm working with some of them there specifically that are doing the turbo machinery side. And so I kind of started out there. I left Tesla in February because I was very interested in this project. I was very interested in getting a lot more time to actually work on generative design. And because that's just a field that interests me a lot. Like if you can reduce the amount of engineering hours, I think you could use those resources for the engineers towards a lot more important things than, like the design as we know it right now.
Right. And at Tesla, you were working on relevant projects, right? With the solar panel placement, I think.
Yeah. So at Tesla, I was doing something similar in regards to design automation, in the sense that I was doing the automation of like where to place the solar panels on the roof, for sunlight, for tree shade, for a lot of different things, for aesthetics, like how good does it look on this roof. And so I was doing a lot of similar things with machine learning and trying to optimize the placement of these panels. And so I actually gained a lot of experience there. And so I was like, okay, I'm interested in engineering automation, and I've had experience doing this in industry with solar.
And so you were playing with these tools, kind of these optimization problems at Tesla, and you left in February because you wanted to get deeper on kind of the tooling side of this, right? And so you started this as like and you said it's a fully open source project right now. And are you imagining it turns into a commercial endeavor, or does it stay open source?
Yeah. So right now, I think it's mainly intended to be open source. I think, right now I'm actually trying to just use it for myself to like actually validate that, okay, I have a compressor design that works in a simulator. If I go build this, does it actually work? And if I can prove that, then I think you could use it for so much more, like so many different applications, not just in aerospace. So that's like something that's pretty exciting for me to think about, which is like, I think right now is the most exciting time in history to be alive, because we're at a point where we have the tools that could automate the design of something, and we have the tools that can automate the manufacturing of something. We have additive manufacturing for like 3D printers, CNCs. So it's really just a matter of prompting what you want, and then it becomes a reality. Right. And so that's like something that like no time in history I would have thought you could do something like this. We didn't have computers. We didn't have automated things like 3D printers. So it's something that excites me to think about.
Right. And how far away are we from being able to kind of think it and express it in language, and then have, like you mentioned the example of have a new type of water bottle or something? Is that
yeah, I don't think that's actually very far off, because there's a lot of code that exists for like, there's like a bunch of CAD archives of like, okay, what does a water bottle look like? Right. What does a gear look like? What does a jet engine blade look like? There's so much resources that could be trained on of what these are. And on top of that, so much code on GitHub of like people that have done parameterizations of different things. And so I don't actually think it's actually too far off to be able to prompt something like, hey, I want a water bottle with the water thing you drink out of on the side or whatever. It's something stupid. You could even prompt it, and it would generate the CAD for that. But like even complicated engineering problems, like I want you to parameterize a gearbox that has 3 gears and 10 teeth on the rightmost gear. And I think even right now it could do something like that. I was playing around with some LLMs, and like essentially you could just tell it like, hey, generate some CAD query code for like a gearbox. And it's not as good now, but I think the more and more code it trains on, we can actually get to a point where something like that exists. And once you can do that, once you can parameterize something, you can optimize it. So that's something that's really interesting.
Right. So how do you think about you mentioned sort of this open source project and all of the different directions it can go. And then you mentioned maybe like a B2B service that has maybe some sort of organization around it, how do you sort of think about the balance between what should be part of the open source stuff and what may be eventually part of this other kind of organization?
Yeah. So I've actually thought about this pretty deeply. I think the thing I'm going to make open source is the engine behind this whole thing. So the CAD generation engine, the simulation engine, making it super easy to plug in your own simulator to this, making it super easy to mesh. So all that is going to be open source. I think what the approach I'm thinking of is making like a marketplace where people can define their parametric models and they could sell those if they want, and the company takes a cut of it. And same way as like every other app store does. And once you can parameterize your problem, I think you can actually make something that's very promising. Like someone wants to like make a fan, or they want to make, I don't know, like a bridge, but there's like a way to parametrically define that someone's already put on the marketplace. You can then take that model and then say like, hey, can you parameterize this bridge such that like, you know, it can handle 1,000 newtons on, or something like that, and it has all the tools to do that.
And is it so? If you're thinking about a marketplace, are the inputs or kind of the supply side of the marketplace things that the tool would not otherwise be able to help me kind of regenerate from scratch?
Yeah. So the idea is that like the reason why you want to parameterize it is you still want to define the problem, because like it's kind of like this, right? So like I think the problem with just starting from nothing is like you start doing like a bunch of iterations for something very basic. Like I think, for example, they're trying to teach like AI, like reinforcement algorithm, how to play like Mario Kart.
Mm-hmm.
And it was just spending like the first like million iterations just hitting the wall, you know? But you actually want to actually get to a point where you have something meaningful, you know? So I think actually being able to describe the problem is very important to actually getting meaningful results. So a parametric model is like anytime you define different parameters for it, it'll always produce something that is valid for that problem. So in the case of like an airfoil, it'll always give you an airfoil shape. And it's just a matter of it simulating that airfoil and then refining those parameters until you get something that is like actually optimal.
And so are you imagining whoever did the kind of original definition and training of that would be like a supplier on the marketplace?
Yeah. So they could create that parametric model and then put that on the marketplace, and then someone could use that towards whatever application they're using. I do think that at some point, once enough of these parametric models are defined, then you could actually do something like an LLM where you don't even need that parametric model anymore because it's seen so many different examples of everything.
Right. Yeah.
And so it can actually just generate that shape. Like you can just go straight from text to shape. That's something that's optimal because it's seen so many examples. And that's just a matter of getting enough data at that point.
Right.
So, yeah.
And so there's kind of at some point that marketplace, the supply of that marketplace could be generated by even newcomers to the marketplace through this LLM, right? So is the marketplace kind of, do you think there's like a time range within which the marketplace is useful to people, after which point the software gets sophisticated enough that it graduates beyond the need for such a marketplace?
I do think still having some sort of parametric model for things is still like very important, because so an LLM can like generate, for example, like the shape, but it could also generate the parameters to that parametric model that are optimal too. And so sometimes, like for example, like you still want the original parametric model and its parameters that the LLM generates, so that you can actually like tweak those and it can actually like, you know, adjust to whatever you're trying to do. The problem is like when you just have it go straight from text to output, like adjusting that is a lot harder. If you just have like, if you're just adjusting XY coordinates, it's a lot harder than just adjusting angles and proportions and like whatever relevant parameters you have to your parametric model.
Right. And what would you kind of mentioned kind of a B2B hypothesis. Do you imagine that there's like software that might be needed by existing manufacturing businesses or design businesses, or like who is it, the people who would typically today use Autodesk, or is it like a different type of customer?
So yeah, every time someone says like, would something like this fit into Autodesk? I kind of just think like it should just replace Autodesk. I think it should just go from spec to CAD. Like there shouldn't be any model designer or like you should just be able to give the parameters you want to a model and it should just generate it. That's the approach to this. I don't think you should actually need a 3D modeler for anything.
And so when you start with kind of the jet engine as I guess like it's your starting point, is that just to sort of have a way to iterate and prove that this can be done? Or do you think that...
Yes, this is a starting point for a very hard problem. Yeah, this is a problem I'm very passionate about that excites me enough to work on this. That is a proof of concept. And who knows, like I find this whole space of aerospace very interesting. It could find something that is very novel, that is like, they could generate something that no one's ever heard of. And I could just go hit the ground running with that alone. But I think I'm using this mainly as a way to motivate myself to actually explore simulation guided design.
Right. And do you think that if you found something novel, you may actually go pursue that? Or would there be a path where you might take these tools and try to help people who are already doing kind of other types of, I don't know, jet or rocket design, maybe somebody in the aerospace industry or many players? Would you ever try to bring these tools to help them improve their processes, or are you just sort of agnostic to the path it takes?
I mean, they can kind of use it for whatever they want. I think I was talking with someone at SpaceX and they're saying like the problem with rocket design is they can use open source tools, but once it gets to actually like wanting to improve the tool, they can't tell you anything because of ITAR. So even though everything I'm doing is open source, they can't actually input what they need. So
you're saying they can't input what they need because it would become part of a open source database? So
ITAR is a weapon and arms regulation through the government. It's like a Cold War era regulation that it's essentially a way that foreign allies or foreign countries can't get a hold of industry trade secrets around defense or aerospace in general. So they could obfuscate or kind of like give an obscure thing like, hey, it would be really nice if like the chamber pressure of this was higher, but they can't really tell you exactly what they need.
You were saying that there's a regulatory reason that somebody might want a compression to a certain spec, but they can't tell what the purpose is. Was that where
they can't tell the purpose? Yeah, because that would technically be like industry secrets, even though it's like very high level. So the problem with ITAR is it's very like ambiguous on purpose. And so there's not really like a definition of what ITAR is other than like, don't release anything on aerospace.
Right.
And so everything I'm doing is just publicly available that I can find in textbooks and like online. But yeah, it's a very gray area, legally speaking.
So do people in the aerospace industry at some point, they have to agree to be under the regulatory structure of ITAR, but maybe you as a software provider, I assume you're not signing up to that yet. Like, is there some threshold at which you'll be...
Yeah, so I think once you start dealing with companies that work specifically with defense or in anything that produces like something that could be deemed as a weapon, then I think ITAR would apply. I've seen similar projects such as mine, like that are in academic sense. This counts as academic work. So it doesn't fall quite under ITAR because it's all like kind of just like it's essentially counts as freedom of speech. So I think where it starts falling under ITAR is when it's no longer open and it's all like set special sauce. And then you actually start having like an advantage in defense to like enemies or like foreign countries that could potentially use this for their own defense. So I think that's the reason mainly.
And so how do you think about sort of the next sequence of things that you want to accomplish, or kind of the next big unlocks that you want to see to sort of, get more conviction for yourself that you're on the right path?
Yeah. So I think, that's why I was thinking about the plugins. So the plugins make it such that I can make the plugins proprietary. And so if you make the plugins proprietary, and you verify that the only people using the plugins are US entities, then you can actually work with those companies directly. They can actually give you their specs, and you can, create something that's meaningful. And so why I was thinking make the plugins is you can have an open source framework that anyone can use as the backend. And then you can have these proprietary plugins that you could use for a lot more intricate stuff that, companies could use.
And do you think that the companies that would be using it today, are they also maybe exploring some of these internally, or is it just kind of not on the radar?
I think they probably are. But I think generative CAD in general is like very new. A lot of aerospace companies I've interviewed at, they're all still using just SolidWorks or some manual CAD tool.
Cool. And the project's called Open Orion, right?
Yep. OpenOrion.org. Yep.
And so everything you can get on the website, are there any of these libraries people can play with right now, or is mostly?
Yeah, right now, if you go to github.com/OpenOrion, all of the libraries I'm using are completely open source. So Turbo Designer is the thing I'm using for generating axial compressors and pumps. There's also a lot of other libraries like Parafoil that you can parameterize airfoils. Paraflow, you can parameterize like rocket nozzles. And the idea eventually is to make it such that all these tools can be like very versatile. So you don't necessarily need to make a whole parametric model for an airfoil. You can just describe what an airfoil is and it'll generate it. So this is kind of the starting point.
Nice. And then is there anything else we should be thinking about, like other areas within kind of ML or generative AI that you think may collide with this, or that might sort of amplify its likelihood of happening faster?
Yeah, so there's definitely this field. So the call I was on earlier was with this person that was a co-author of the book Physics-Based Deep Learning. I think that's the biggest thing for what I'm doing right now. It's the idea. So traditional deep learning is you're taking in a lot of data, and you're essentially trying to fit a line to it. That's essentially most of ML. It's just fitting a line to something. People want to like call it magic or whatnot, but at the end of the day, it's like literally just y equals mx plus b. M being the slope is the weights, and b being the bias. So like, essentially on the y-intercept, where is this line being fit? The problem with a lot of physics problems is they're not always linear. You have a lot of nonlinear problems. And so what physics-based deep learning does is it allows a lot of physics-based principles to be applied in the training process. So instead of training directly on the ground truth data, you're training with the simulator in the loss process. So there's these things called differentiable simulators that you can actually get this concept of loss, of like how different is the prediction versus the thing it outputs. And you can actually more accurately get the loss directly from the simulator rather than a bunch of ground truth data that the simulator outputs. Because when the simulator outputs the data of like what the simulation data is, all of that data of like how it got there is lost. But with machine learning, like a lot of the stuff it does to get the gradients for getting lost is going backwards. So like this thing called backprop, which is getting like all the different steps and then getting like a gradient of like change of like how all these things change to get to the output of it. And so that's kind of the approach I'm trying to go with this project, which is like a more of a physics-based deep learning approach rather than standard like supervised learning. So that's a main field of ML I think I'd like to explore with this.
Great. Well, thanks for sharing everything you're working on. It's exciting. I want to follow along and keep track of how progress is going. So keep me posted, and let's do a recap after made some more progress and hear how things are going.
Thank you so much.